Tutorial 11, Weather Theory. This lesson will cover weather theory. Understanding the theories behind weather helps a pilot make sound weather decisions based on the reports and forecasts obtained from a flight service station weather specialist and other aviation weather services. In any given volume of air, nitrogen accounts for 78% of the gases that comprise the atmosphere, while oxygen makes up 21%. Argon, carbon dioxide, and traces of other gases make up the remaining 1%. This cubic foot also contains some water vapor, varying from 0 to about 5% by volume. This small amount of water vapor is responsible for major changes in the weather. The atmosphere is made up of 4 distinct layers that extend up to 350 miles from the Earth's surface. The first layer is the troposphere, which extends from the surface to 20,000 feet over the poles and 48,000 feet over the equator regions. Most weather happens in this region, and the temperature drops by 2 degrees Celsius for every 1,000 feet of altitude gain. The pressure also drops by an inch for every 1,000 feet of altitude gained. Above the troposphere and before the stratosphere, there is a region called the tropopause. This region traps moisture in the troposphere and the associated weather. Above the tropopause are 3 more atmospheric levels. The first is the stratosphere, which extends from the tropopause to a height of about 160,000 feet. Little weather exists in this layer, and the air remains stable, although certain types of clouds occasionally extend in it. Above the stratosphere are the mesosphere and thermosphere, which have little influence over weather. The atmosphere is in constant motion. Certain factors combine to set the atmosphere in motion, but a major factor is the uneven heating of the Earth's surface. Earth is warmed by energy radiating from the sun. The process causes a circular motion that results when warm air rises and is replaced by cooler air. Because the Earth has a curved surface that rotates on a tilted axis while orbiting the sun, the equatorial regions of the Earth receive a greater amount of heat from the sun than the polar regions. Solar heating causes higher temperatures in the equatorial areas, which causes the air to be less dense and rise. As the warm air flows toward the poles, it cools, becoming denser, and sinks back toward the surface. The unequal heating of the Earth's surface not only modifies air density and creates circulation patterns, it also causes changes in air pressure, or the force exerted by the weight of air molecules. Although air molecules are invisible, they still have weight and take up space. Imagine a sealed column of air that has a footprint of 1 square inch and is 350 miles high. It would take 14.7 pounds of effort to lift that column. This represents the air's weight. If the column is shortened, the pressure exerted at the bottom and its weight would be less. The weight of the shortened column of air at 18,000 feet is approximately 7.4 pounds, almost 50% that at sea level. The actual pressure at a given place and time differs with altitude, temperature, and density of the air. These conditions also affect aircraft performance, especially with regard to takeoff, rate of climb, and landings. The force created by the rotation of the Earth is known as the Coriolis force. This force is not perceptible to humans as they walk around because humans move slowly and travel relatively short distances compared to the size and rotation rate of the Earth. However, the Coriolis force significantly affects bodies that move over great distances, such as an air mass or body of water. The Coriolis force deflects air to the right in the northern hemisphere, causing it to follow a curved path instead of a straight line. The amount of deflection differs depending on the latitude. It is greatest at the poles and diminishes to 0 at the equator. The magnitude of Coriolis force also differs with the speed of the moving body. The greater the speed, the greater the deviation. As shown above, the speed of the Earth's rotation causes the general flow to break up into 3 distinct cells in each hemisphere. This circulation pattern results in the prevailing westerly winds in the conterminous United States. Circulation patterns are further complicated by seasonal changes, differences between the surfaces of continents and oceans, and other factors such as frictional forces caused by the topography of the Earth's surface, which modify the movement of the air in the atmosphere. Thus, the wind direction at the surface varies somewhat from the wind direction just a few thousand feet above the Earth. Atmospheric pressure is typically measured in inches of mercury, Hg, by a mercurial barometer shown on the left. The barometer measures the height of a column of mercury inside a glass tube. A section of the mercury is exposed to the pressure of the atmosphere, which exerts a force on the mercury. An increase in pressure forces the mercury to rise inside the tube. When the pressure drops, the mercury drains out of the tube, decreasing the height of the column. This type of barometer is typically used in a laboratory or weather observation station, is not easily transported, and difficult to read. An aneroid barometer, shown on the right, is an alternative to a mercurial barometer. It is easier to read and transport. The aneroid barometer contains a closed vessel called an aneroid cell that contracts or expands with changes in pressure. The pressure-sensing part of an aircraft altimeter is essentially an aneroid barometer. It is important to note that due to the linkage mechanism of an aneroid barometer, it is not as accurate as a mercurial barometer. To provide a common reference, the International Standard Atmosphere, ISA, has been established. These standard conditions are the basis for certain flight instruments and most aircraft performance data. Standard sea level pressure is defined as 29.92 inches of mercury and a standard temperature of 59 degrees Fahrenheit, 15 degrees Celsius. Atmospheric pressure is also reported in millibars, with 1 inch of mercury equal to approximately 34 millibars. Standard sea level pressure is 1013.2 millibars. Typical millibar pressure readings range from 950 to 1040 millibars. Since weather stations are located around the globe, all local barometric pressure readings are converted to a sea level pressure to provide a standard for records and reports. To achieve this, each station converts its barometric pressure by adding approximately 1 inch of mercury for every 1,000 feet of elevation. For example, as shown above, a station at 5,000 feet above sea level with a reading of 24.92 inches of mercury reports a sea level pressure reading of 29.92 inches of mercury. Using common sea level pressure readings helps ensure aircraft altimeters are set correctly, based on the current pressure readings. As pressure decreases, the air becomes less dense or thinner. This is the equivalent of being at a higher altitude and is referred to as density altitude, dA. As pressure decreases, dA increases and has a pronounced effect on aircraft performance. Altitude affects every aspect of flight, from aircraft performance to human performance. At higher altitudes, with a decreased atmospheric pressure, takeoff and landing distances are increased, as are climb rates. When an aircraft takes off, lift must be developed by the flow of air around the wings. If the air is thin, more speed is required to obtain enough lift for takeoff. Therefore, the ground run is longer. An aircraft that requires 745 feet of ground run at sea level requires more than double that at a pressure altitude of 8,000 feet, as shown in the figure above. At sea level, atmospheric pressure is great enough to support normal growth activity and life. By 18,000 feet, the partial pressure of oxygen is reduced and adversely affects the normal activities and functions of the human body. The reactions of the average person become impaired at an altitude of about 10,000 feet. But for some people, impairment can occur at an altitude as low as 5,000 feet. The physiological reactions to hypoxia or oxygen deprivation are insidious and affect people in different ways. These symptoms range from mild disorientation to total incapacitation, depending on body tolerance and altitude. Supplemental oxygen or cabin pressurization systems help pilots fly at higher altitudes and overcome the effects of oxygen deprivation. Air flows from areas of high pressure into areas of low pressure because air always seeks out lower pressure. In the northern hemisphere, the flow of air from areas of high to low pressure is deflected to the right and produces a clockwise circulation around an area of high pressure. The opposite is true of low pressure areas. The air flows toward a low and is deflected to create a counterclockwise circulation. High-pressure systems are generally areas of dry, stable, descending air. Good weather is typically associated with high-pressure systems for this reason. Conversely, air flows into a low-pressure area to replace rising air. This air tends to be unstable and usually brings increasing cloudiness and precipitation. Thus, bad weather is commonly associated with areas of low pressure. A good understanding of high and low pressure wind patterns can be of great help when planning a flight, because a pilot can take advantage of beneficial tailwinds shown above. When planning a flight from west to east, favorable winds would be encountered along the northern side of a high-pressure system or the southern side of a low-pressure system. On the return flight, the most favorable winds would be along the southern side of the same high-pressure system or the northern side of a low-pressure system. While the theory of circulation and wind patterns is accurate for large-scale atmospheric circulation, it does not take into account changes to the circulation on a local scale. Local conditions, geological features, and other anomalies can change the wind direction and speed close to the Earth's surface. Different surfaces radiate heat in varying amounts. Plowed ground, rocks, sand, and barren land give off a large amount of heat. Water, trees, and other areas of vegetation tend to absorb and retain heat. The resulting uneven heating of the air creates small areas of local circulation called convective currents. Convective currents cause the bumpy, turbulent air sometimes experienced when flying at lower altitudes during warmer weather. On a low-altitude flight over varying surfaces, updrafts are likely to occur over pavement or barren places, and downdrafts often occur over water or expansive areas of vegetation, like a group of trees. Typically, these turbulent conditions can be avoided by flying at higher altitudes and even above cumulus cloud layers, as shown by the image above. Convective currents are particularly noticeable in areas with a landmass directly adjacent to a large body of water, such as an ocean, large lake, or other appreciable area of water. As shown by the top images, during the day, land heats faster than water, so the air over the land becomes warmer and less dense. It rises and is replaced by cooler, denser air flowing in from over the water. This causes an onshore wind, called a sea breeze. Conversely, at night, land cools faster than water, as does the corresponding air. As shown by the bottom image, the warmer air over the water rises and is replaced by the cooler, denser air from the land, creating an offshore wind called a land breeze. Convective currents can occur anywhere there is uneven heating of the Earth's surface. As shown above, convective currents close to the ground can affect a pilot's ability to control the aircraft. For example, on final approach, The rising air from terrain devoid of vegetation sometimes produces a ballooning effect that can cause a pilot to overshoot the intended landing spot. On the other hand, an approach over a large body of water or an area of thick vegetation tends to create a sinking effect that can cause an unwary pilot to land short of the intended landing spot. Obstructions on the ground affect the flow of wind and can be an unseen danger. Ground topography and large buildings can break up the flow of the wind and create wind gusts that change rapidly in direction and speed. These obstructions range from man-made structures like hangars to large natural obstructions such as mountains, bluffs, or canyons. It is especially important to be vigilant when flying in or out of airports that have large buildings or natural obstructions located near the runway. The intensity of the turbulence associated with ground obstructions depends on the size of the obstacle and the primary velocity of the wind. This can affect the takeoff and landing performance of any aircraft and can present a very serious hazard. During the landing phase of flight, an aircraft may drop in due to the turbulent air and be too low to clear obstacles during the approach. This same condition is even more noticeable when flying in mountainous regions. As shown above, while the wind flows smoothly up the windward side of the mountain and the upward currents help to carry an aircraft over the peak of the mountain, the wind on the leeward side does not act in a similar manner. As the air flows down the leeward side of the mountain, the air follows the contour of the terrain and is increasingly turbulent. This tends to push an aircraft into the side of a mountain. The stronger the wind, the greater the downward pressure and turbulence become. Before conducting a flight in or near mountainous terrain, it is helpful for a pilot unfamiliar with a mountainous area to get a checkout with a mountain-qualified flight instructor. Please help us spread the word about Pilot Training System, and we look forward to further servicing your flight training needs.